Hello everyone. So today is week 11 and we are trying something different this week. So I'm remote and then try to give a lecture through online, and then you are in the classroom and then you will interact with your peers and TAs. So I hope this mechanism works, and then I'll be back in the classroom next week. Okay, so today's topic is shear force diagram and bending moment diagram. Very, very important. So we'll define the sign convention of beam's internal forces and determine the internal forces of a point of beam by solving equilibrium equations. So this is kind of using application of what we learned so far. And then the third one is new, plotting the shear force and bending moment diagram of beams under point load, distributed load, and a bending moment. Okay, so now we are dealing with beams. So beam is a horizontal member that carries vertical load. So horizontal member that carries vertical load like passengers or vehicles, right? And then for beam analysis, we can use equivalent equations, 3 equations in 2D, right? And then we'll use method of cut. So at the cut section, we will find the unknown forces by solving equilibrium equations. So at the cut section, we have 3 internal forces. So first one, normal force. So normal force is N here, so F in here. So this direction, so it's axial force, another word, axial force. And then shear force, V is perpendicular force to the member. And the bending moment is moment acting upon the cut section. So there are 3 internal forces. Okay, and then sign convention of these 3 internal forces are very important. So I give you the positive sign convention. So for the normal force or axial force, we know the tension, right? Tension is positive and compression is negative. So tension, normal force, axial force, tension is positive. And therefore shear force is tricky. So so it's a pair of force, um, and right side downward, left side upward. So that is positive. So it's kind of tricky, but when we think about the cut section here, then when we plot V at the cut section, so like this, right? And then that is positive direction. So downward from the left side and then upward from the left side, right? So that is positive shear force. And then bending moment, so also a pair, clockwise left and then counterclockwise right. So that is positive. And then that is using the example of a beam, right? So if we have horizontal member and then if there is a force, like my calculator is on top, right? Then it is inducing this kind of curvature, right? So that is defined as positive moment. So that means this direction, right? So this direction is positive bending moment. So right side, so smiley face, think about smiley face, right? So that moment, a pair of moment inducing this kind of curvature is positive. And why is it important? Because this sign convention will be used in shear force and bending moment diagram later, and that matters, right? So let's define and then make sure we understand and then know the positive direction of all 3 internal forces. Okay, our first clicker quiz. So I show you again. So this is positive tension, and then at the cut section V or bending moment, right? It's positive. And then what is the correct pair of signs of the internal forces? So this is the direction of 3 internal forces, right? And then what do you think? Is this N positive? Is this V positive? And is this M positive? What's the correct pair among A, B, C, D? Okay, great. So let's see the result. So we have A and C kind of divided and a few B and D. Okay, so let's check the sign convention once more. So normal force, tension, shear force, V, and then bending moment like this. So is this tension? Yes. So tension, so it is positive, so not B. And then what about V? At the cut section, we should plot V like this, right? So downward should be positive, and then this is now negative, right? So this is positive and this is negative. So these two are correct, right? And then what about moment? This is correct. This is positive, right? So this moment should be positive. So C is correct. And then when we see the result again, A, okay. So we also, this confirms that sign convention for V is most tricky one, right? So I'll repeat, positive shear force is down from the right and then upward from the left. So this is positive shear. I think normal force and moment is fine. So please review the positive sign convention of the shear force. Okay, let's move on. Yep. So now using this sign convention, we can analyze beam using method of cut. Okay. So we are given this beam. It has three forces and then 3-point loads and then two discrete loads. And we want to know the internal forces at the cut section at C. Okay. Then we'll cut this and they use either side of the structure, right? So first, step one is calculate the support reaction, right? And then second, make a cut, and then think about the equilibrium of either side of the structure. Also using equilibrium equation using these three equations. So it's two-step procedure like truss or machines or frames. Okay, so then what is the shear force and bending moment diagram? So we talked about three internal forces at the cut section. So the normal force, shear force, and then moment. And if we cut many sections and then um, connect those lines, calculate the shear force or bending moment, right, and then many points, and then connecting those dots together, then that's the shear force or bending moment diagram. So that's these diagrams are variations of the shear force and bending moments of a beam as a function of distance, right? So if we have this beam here, right, and there are two forces, then we can cut here and then solve three Coulomb equations, right? So if we cut here, then we'll use left side structure, right? And then left side structure, we only have 20 kilonewtons, so 20 kilonewtons is added. And then at the cut section, we add unknown internal forces. Technically, we should add three. So N1 and then V1 and M1, and then solve three equilibrium equations, right? So what do we have? Fx equation, so n1 is 0, right? And the fy equation, what do we have? Minus 20 minus v1 equals 0, so we can find v1 is minus 20. And then also moment equilibrium equation at the cut section, right? Then we have moments 1 only, so this one is 0, something like that. So we'll solve the problem again. But at each cut section, we'll solve these three equations and find out what are these three internal forces. So that is method cut. Okay. And then we can cut before B, after B, before this 40, after this 40, and then before D, something like that. You can choose the number of cut sections and then think about equilibrium, solve these three equilibrium equations per cut section, and then find out of V1 to V6 M1 to M6. And in this case, normal forces are all 0, so it's trivial. And then those found points are connected together like this, and then this upper chart is the shear force diagram, and the lower chart here is bending moment diagram. Okay, so this is how we plot the shear force and bending moment diagram using method of cut. Okay, so any questions? Okay, is muted. So Billy, if you have any questions from students, you can write the question in the chat box or pass the microphone to student. Okay. Okay, so far it looks like no one in the podium, so I keep going. So you see here, if we use method of cut, it's a lot of work. We need to cut and then solve the equation many times. So the recommended method is so-called graphical method, especially for a beam with only point load. Then we can use so-called follow the load method. So what is this method? We can start from 0 from the shear force diagram and then follow the load direction and the magnitude and then plot the shear force diagram. So at A, we have 20 kilonewton, right? And then direction is downward, so we go down by 20. So this is 20 kilonewton. Go down, so it should be minus, right? And then at B, we have 46 kilonewton upwards. So from minus 20, we go up, right? We go up. So this is 46 kilonewton, and then it results in 26 kilonewton, right? And then between B and C, there's no vertical load, so it stays there, stay constant, right? And then at C, 40 kilonewton downwards. So from 26, we go down by 40, and then it's minus 14. And between CD, no changes, stay there. And then at D, we have 14 kilonewton upwards, so go up by 14 kilonewton going back to 0. So that's follow the load method. And then I recommend using this method if you have a beam with point load only. Okay. Okay. Then now let's check with the clicker quiz. So what is the shear force at the blue point in the figure? So blue point is here. Okay. And then we know there's 32 kilonewton here, and then AY is 17, and then BY is 15. So I start the clicker quiz. And then for this, please check, discuss with your peers and then find one answer. Is it 32 kilonewton or 17 or 15 or 0? So I let you know the cut section again. So blue point is here. So this point, what is the shear force? So that is V, right? So shear force, what is the shear force? Internal forces perpendicular to the beam. Okay, great. Wow. So we have 6A, 100B, 48C, and 31D. So let's figure out what that is. So at this point, we only learn method of cut or graphical method. So if we cut here, and then think about the equilibrium of the left side member section, right? And then plot the free body diagram, right? And then free body diagram, what is free body diagram? We include the reaction here, and then what is V1, and then M1 for the left hand cut section, right? And then solve Fy equation, right? And if upward is positive, then we have 17, and then V1 equals to 0, right? So then V1 is 17 kilonewton. So B is correct, right? So 100 students, yep, you're right. And then if you chose 32, it's not because there is a reaction here, right? And then we should use this one. And then if you use the right side structure, we should consider 32 as well as 15. So it should be 17 again. right? And then 15 is too far, right? And then 0, there is a load, right? If there's a load, then there should be some vertical forces, except for special cases. Okay, so great job. Let's go back to the last learning objective. So using the relations between shear and bending moment, how to plot shear force and bending moment diagram. So this is the relation between the load, discrete load, shear force, and the bending moment. So what relations? It's related by integral. So if we have discrete load W, then integration of the load is shear force diagram, and then integration of the shear force is the bending moment. Okay, and then the other direction is differentiation, right? And the graphical meaning is here. So this is important. So from slope of the moment diagram is the shear force. And then slope of the shear force diagram is the discrete load. And then what is the other direction? It's area, right? So area under the load is the changes in shear force. This is area, right? Area. And then area under the shear force is the bending moment. Right. So that's the relationship between the discrete load, shear force, and bending moment. And then we will use this one to solve the second problem later. Okay. And this special case, so effect of a concentrated moment in the middle of beam. So if we have some kind of moment, so moment M0, so two keep fit, something like that, right? And it is acting at B. What happens is what's effect on shear force diagram? No effect because moment is higher order term, higher dimension. But in the bending moment diagram, clockwise bending moment is affecting the bending moment diagram jump up. So if we have two keep fit moment at B, right? And then if this is moment diagram, then moment diagram should jump up by 2 keep fit, right? So, and counterclockwise, jump down. Clockwise, jump up. So only remember the first one. Clockwise, you see clockwise movement, it jumps up in the middle of the beam. And if it is the side, then we should follow the sign convention. What is the sign, positive sign convention? This one, right? This is positive sign convention. In the middle, clockwise, a clockwise movement is jumping up. Okay. Okay, then I think this is the last clicker quiz. So it's about the moment. Yeah, using the sign convention. What is bending moment at A? At A is left hinge, and then we see 12 kilonewton meter moment here, and then 9 kilonewton force, 18, and then 3 kilonewton meter moment at D. So what do you think? Is it 27 or 12 minus 12 or 9? So I plot the sign convention here again. And then we are interested in A only. So this one also, please feel free to discuss with your friends, peers. Okay, I'll close after 10 seconds. Okay, great. So we have C, the most votes, B next, and then A for A and D. Okay. So at A, it is kind of left hinge and that it has only this moment, 12 kilonewton meter, right? And then the question is this moment positive or not? And then it is left side of the member, so we should use this sign convention, and clockwise is positive, and then now this is the opposite direction, so C is correct. Okay, so absolute value 12 is right, but using the sign convention, this is negative, so it should be minus 12 kilonewton meter bending moment and the bending moment diagram. Okay, so let's start problem solving. So I brought two problems. First one is a cantilever with multiple point load, and the second one is a simply supported beam, right? And for the first one, I tried to use method cut to give you some concept behind the shear force and bending moment diagram. So here for the beam and loading shown, draw the shear and bending moment diagrams. B. Determine the maximum absolute values of the shear and bending moment. And this is cantilever beam. And then we have full load, right? So as mentioned before, the beam analysis is also two-step procedure. So we should first find the reactions and then plot the diagrams, right? So then A is open end, so no reactions, and then B is fixed. So we should have BX and then BY and moment at B, so MB. So three reactions at the fixed joint. So I'll add step 1. And we'll solve three Coulomb equations to find those reactions at B. Okay. Okay, then BX, so what is BX? It's very difficult to hear. Billy, can you turn on wireless microphone or microphone somehow so that I can hear student response? Yep.
You can hear?
Yes, I can hear. Yep. Okay. So what's BX? Anyone? 0, yes. Fx equals to 0, and then there is no horizontal force, so Bx is 0. Okay. And then we can try Fy too. If upward is positive, then we can count all the loads together. So 15 down minus 15, and then 25 down, right? And then 20 down, 30 up, and then by up, right? So then we can find by is 30 kilonewton. Okay, and then move on to moment equilibrium equation. You can use any point as reference, but I like to use B here, and then counterclockwise is positive, and moment by Bx and By, 0, but we need to add moment at B, either add or subtract, but we assume the counterclockwise is positive, and this is also counterclockwise, so it's plus MB. And moment by 20 is 20 times momentum from B to E, so that's 0.8. And plus, because at this point, 20 kilonewton is inducing counterclockwise movement, right? So that's how we determine, right? And then for 30 kilonewton is the opposite direction, so 30, and moment arm from B to 30 is 0.8 plus 0.4, so it's 1.2. And next, 25 plus 25 times, so this is 0.3, right? 843, right? So 1.5. And the last one, 15 times 1 plus 0.3 plus 0.4 plus 0.8. So it is 2.5. Right? Is there anything else? 1, 2, 3, 4, and m. No. So then by solving this equation, we can find MB. So I'll give you a few minutes to calculate this. And then my calculation is 55 kilonewton meter. It should be negative, right? So it's minus 55 kilonewton meter. So these three are the reaction at this fixed support. Okay, then step 1 is done, and we move on to step 2. So using method of cut, we will find the internal forces. Okay, so I clean up here. Okay, and then where to cut? Where to cut? Before or after some forces. So in this case, let's cut after each load. So after this one, this distance is very, very small, just right after 15 kilonewton, right? And then right after 25, right after 30, right after E. Okay, so let's try these 4 sections. Let's say this is 1, 2, 3, 4. And then at each cut section, we'll solve the equilibrium equations. Okay, and I prepared this cut section for my convenience. So, so let's try first. First cut section. So maybe I use a little bit bigger. Right. Okay, then the first cut section. Now this distance is very small, and we have 15 kilonewton here, right? And then at the cut section, we add unknown internal forces using the positive direction. And I mentioned that we can add N1, but if there's no horizontal forces, external forces, then N1 is 0, so we don't have to consider. So typically for beam, horizontal reaction is 0 because there's no horizontal external forces. But if there is, then we need to add. Okay, then shear force, which one is positive, upward or downward, based on sign convention? Upward, downward?
Down.
Downward, thank you. Downward is correct. And then what about movement? What is positive movement? Clockwise or counterclockwise? Clockwise? Counterclockwise? Think about this, right? Which one is positive here? This direction, right? So counterclockwise is positive. So let's use this positive direction and solve the equilibrium equation. So Fy first, we will not solve fx because it's trivial. Fy equation, upward is positive. It's so simple. We have 15 down and then V1 down. So V1 is minus 15 kilonewton. So I speed up and I upload everything. So yeah, don't worry about class note. Please follow me instead. Okay, and then moment equivalent equation about this cut section. Okay, so I add this one as x, cut section, cut, right? And then counterclockwise is positive. Then we add m1 as is because it's positive, assumed as positive direction, right? And then moment induced by 15 kilonewton. So 15 kilonewton times this distance. What if this distance is very, very small, 0.000001 meter? Then the moment induced by 15 kilonewton is negligible, right? So then it is zero. So m1 is zero because of this distance. So we found these two already, and then we can keep going for another 3 sections, right? We have 3 sections. Okay. Okay, so maybe I'll add. Okay. So second section, we have 15 kilonewton and 25 kilonewton here, and then this is cut section, right? And we add same direction with different variable, V2, the same direction, and then M2. And then we'll solve Fy equation again. So the same procedure, so let's try this one again with me. So then 15 downward, 25 downward, and then V2 downward. So then V2 equals to minus 40 kilonewton, right? So Fy is done. And then moment at the cut section. So cut section is here. Counterclockwise is positive. That we add M2 as is. That's why we assume M2 as counterclockwise direction. And then what about the moment induced by 25? 25 times this small distance. If this small distance very small, moment effect is zero, so that's good. And then now 15 kilonewton is inducing moment. 1 meter is not negligible, so 1. And then based on this point, this force is inducing counterclockwise moment, so it's positive, right? So then M2 is also found, it's minus 15 kilonewton meter. Okay, any questions? Now that you have many TAs around, please feel free to ask questions to TAs Hernan, Billy, Tom, and Max and Jeff. Okay. Okay, then third cut section and fourth cut section, I'll give you about 2 minutes to solve equivalent equation. But I give you the direction of unknown to unknown here, V3, M3, unknown here, V4, and then M sub 4, right? And then for that, please solve these 2 equations. So this X is cut section here. And then this is cut section here. So after 2 minutes, let's compare it together. So TAs, please go around and then answer student question and then I hope you are getting there. So I'll share what I have. So for the third one, I have 15 down, 20 down, 30, and then V3 down. So V3 is minus 10 kilonewton. And then for the moment, so I'll use a little more space. We include M3 as is, right? And then no moment induced by 30 because it's too short, right? And moment by 25 is 25 times 0.3. And then moment by 15 is 15 times 1.3, right? So from this equation, we can find M3 is minus 27 kilonewton meter. And then last one, Fy equation, if upward is positive, then we have minus 15, minus 25, plus 30, and minus 20, and minus V4, right? So V4 is now minus 30 kilonewton. And the last one, moment from this one, right? So then also with the same reason, this distance too small, right? So no moment effect by the force right adjacent to that point, right? So then moment by 30, we need to add M4 first. Sorry about that. M4, and then moment induced by 30 is 30 times, what is this distance? 0.4? 8? Yeah, 0.4, right? So it's E, so 0.4. So minus 30 times 0.4. And this plus 25 times from here to here, 0.4 plus 0.3, 0.7. And the last 15 times from here to here, 1.3, 0.4, 1.7, right? So let me check. Okay, yep, that's right. And then M4 is now minus 31 kilonewton meter. Okay, so I'll show you section 3 and 4 again. So V3 is minus 10, M3 is minus 27, V4 is minus 30, and then M4 is minus 31. So did you get these numbers? Okay. Okay. Then now we are done with finding these points, and then time to plot the shear force and bending moment diagram. So let's check. So these are what we have here: V 1, 2, 3, 4, M 1, 2, 3, 4, and then what we have at the fixed connection B, it was By was 30 kilonewton up, and then moment at B is minus 55, right? So we assume this one, and then it's minus, so it is different direction. So this direction, and then this is 55 kilonewton meter. So this is the free body diagram, and then this is the table. Okay, and now before plotting, think about the sign convention. Shear force, positive shear force like this, and positive bending moment like this. Okay, based on our sign convention, is this plus 30 or minus 30? We should see right side of the section. So this is what we need to see. And then is it the same direction or opposite direction? Opposite direction, right? So it's minus 30. And about the moment, Is this plus 55 or minus 55? You see this one again, right? And then that's the opposite direction, so it's also minus 55. So we should find these numbers, shear force and bending moment, based on the sign convention, and then move on to shear force and bending moment diagram. So here, space line here, shear force V, right? And then this is A, C, so A, C, D, E, and B, right? And then we have right after A minus 15, right? Right after C minus 40, right after D minus 10, slightly, right? So this is minus 10. And then right after E minus 30, like this. And then at B, we have minus 30 as well, right? So these points are what we have right now, okay? And then we know if there are no shear forces, no changes, right? So we can say stay there between AC, stay there between CD, DE, and then EB, right? So then we can just use some guidelines like this, connecting dots together, right? So that's the shear force diagram. Any questions? So that's using the method using method cut. And here we can also use the follow the load method, right? Follow the load method. How? You can just follow. So at A we have 15 down, so down by 15, and then stay there for between AC, right? And then C down by 25 from 15 to minus 40. Between CD, no changes. And then D, 30 kilonewton up, so up by 30, so minus 10. DE, no changes. And the E have 20 kilonewton down, so minus 10, minus 20, minus 30, no changes. And then this is the number, right? So that's a follow the load method, and it's much, much faster, right? Okay, then now bending moment diagram. So here, again, baseline moment. Yep, so and then this is A, this is C, this is D, this is E, and then this is B, right? And then we have these 5 points. So at 1, we have 0. At 2, minus 15. 3, minus 27, so less than twice. And then minus 31, a little bit lower. And then minus 55. So here, minus 55, right? And then now for a moment, we can connect these dots together, something like this, 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 and this, right? And then moment at B is minus 55. Okay, any questions? Yep. I feel the biggest drawback of this system is I cannot get your questions quickly, yeah, enough. Okay. So next week I'll be back. So let's have more interaction next week. And then move on to the second problem. So it is more complex problem, and I think good problem to review shear force and bending moment diagram method, graphical method. So here we have simply support beam with A pin and B roller. And we have 2 concentrated moment and then 3 point loads. We need to draw the shear and bending moment diagrams and determine the maximum absolute values of the shear and bending moment. Okay, fair enough. So Let's start step one. Step one is finding the reactions. So AX, AY, and AX, but there's no horizontal force, so we know AX is 0, so I'll not include it here. And then BY, unknown. Okay? And then start with moment equilibrium equation. You have freedom to choose either A or B because each point, each support has only one unknown. So if we use A as unknown and assume counterclockwise positive, then let's solve the moment equation. So at A, we have 6 kips per feet here. What should we do? Is 6 times something? Or is plus 6 or minus 6? What do you say? Can you repeat?
Minus.
Minus 6. Any other opinions? Plus 6 or 6 times something? Oh, is it consensus? Minus 6? Okay, it looks like it's consensus. Okay, so we can subtract minus 6. Why? Because of sign convention, right? So I think you compare this one with this one and it's opposite and then use minus, right? Is it the logic you used? And the answer is no, this is positive. This is positive. Why? So I'm very glad that I hear that. Why? It's bending moment. So it's moment equal equation. We solve this one, yeah, for multiple weeks, and then we define the sign convention within this moment equal equation here with our freedom, and we assumed counterclockwise positive. And then within the equation, this sign convention doesn't matter. You don't have to consider this one. It's convention we defined within the moment equilibrium equation. And then we assume the counterclockwise positive, and this is counterclockwise. So that's why this is plus. So plus 6 is correct. This is not confusing. There are two sign convention. One is this. So this is temporary. It is it is correct within moment equilibrium equation. And then this is correct for the diagram, bending BMD, so bending moment diagram sign convention. So these two are different. Okay, so please make sure you understand that. And then now move on to calculating moment from this one. So minus 2 times 6 because it is inducing clockwise moment based on A, right? And now 3 times 12 because this point is also inducing clockwise moment and moment arm is 6 plus 6, 12. And then 4 minus 4 times 18, right? So it's also clockwise moment, inducing clockwise moment, and distance from A to E is 18. And the last one, by times 24, and it is inducing counterclockwise, is plus. And now, what about this 12? Is plus or minus? Plus 12 or minus 12? Plus 12. Yep, thank you. And then now within this equation, we have only one variable, that's by. So we can find by. Okay, so it's 126. So I'll give you the number by. So by is 4.25 kips. Okay, and then here, I like to emphasize this plus 6, 12, 6, based on the sign convention. That's absolutely correct within the moment equilibrium equation. Moment equilibrium equation, yes. And then next, we'll solve the second equilibrium equation. Also, this sign convention is true within this equilibrium equation. You don't have to think about sign convention of the shear, okay? And now we have AY unknown, 2 down, 3 down, 4 down, and BY, so that's 4.25, right? So I use 4.525 up front. And we can find AY is 4.75 kips. I'm sure you are familiar with FY equation, so I went through very quickly. And then now step 2, we'll plot the shear force diagram. Okay, so let me clean these up, and then replace the unknowns with actual number. AY is 4.75, BY is 4.25. Okay, and then shear force A, B, and then it's mid span and quarter span like this, right? Okay, and then it's all point load, so let's use follow the load method. So at A, we have 4.75 upward, so 4.75 upward. And between AC, no changes, right? No changes, so stay there. At C, we have 2 kips downward. So from 4.75 down by 2. So this one should be 2.75. Okay. And then between C and D, no changes. So stay there. And then at D, we have 3 kips downward. So from 2.75 down by 3. So going to minus, right? So it's minus 0.25. And then between D and E, no changes. And then at E, we have 4 kips downward. So down by 4. So it's minus 4.25. And between E and B, no changes. And then BY is 4.25. So going up by 4.25, going back to 0. So this is shear force diagram. And then shear force diagram always start with 0 and then should end at 0. So that's how you check your diagram is correct as well. Okay, and then now bending moment diagram, right? So bending moment diagram here, moment, and then mid span, quarter span, right? And then we'll use graphical method. So from the shear force to bending moment, it's integration, right? So area under the shear force diagram is changes in the bending moment. So then we need to find the area under these rectangles. And that is really simple, so I'll give you the numbers. So the first area is 28.5. So all circled numbers are the areas. Here, 16.5, and here, 1.5, and here, 25.5. And also it's integral and then differentiation. Sign matters, so I'll indicate the sign here. Plus, plus, minus, minus. Because integration of shear force is bending moment, that means shear force is the slope of the bending moment. And if slope is positive, what do you mean? What does it mean? Positive slope means increase or decrease. Positive slope, increase, right? And then negative slope is decrease, right? So that's what we can get from here. And areas here are changes of the bending moment, okay? And then initial point. What is the bending moment at A? We have 6 skips this direction. And now it's time to use the sign convention of the bending moment. So this one. Is it +6 or -6? It's now -6, right? It's different, right? The opposite direction. So we start with -6. We must use sign convention of the bending moment diagram. When you draw the bending moment diagram, okay, start with -6. And then now the changes of bending moment between A and this point is 28.5 plus slope increasing. So from -6, it's increased by 28.5. So it's 24, yeah, 22, yeah, 22.5. Okay, right? Increased by 28.5, right? And another thing, so slope is constant here. Plus and slope is constant. And then what is the integration of constant function? Is it linear, quadratic, or cubic? Constant. Slope is 0, so it's linear function. So it should be linearly increasing like this. Right? So that's how you plot the bending moment diagram using the relationship between shear force and bending moment. Okay, then now moving on to next part. So the second part, the changes of bending moments is 16.5 is increased, right? So from, yeah, so let me erase this one and then write down here. Okay, and then increased by 16.5, so then that is 39. And again, shear force diagram is constant, so it's linearly increasing. This, right? And then next portion is negative slope, so that means it's decreasing. So decrease by 1.5 from 39, right? So that's 37.5, and then also linearly decreasing, something like this. And the last portion, changes of moment 25.5, and then it is decreased, so decreased by 20.5 from 37.5. So that's 12. And constant slope, that means linear, something like this. It doesn't go back to 0, right? And is it okay? And we need to go back to our original problem and then check whether we have moment at B. Yes, we have moment at B. That's 12, keep it. And then this direction. Is this plus 12 based on sign convention here? Right side, right side. It's the same direction, right? It's correct, right? So you found plus 12, 12 is the final moment, and then that is the answer. And then what is the absolute maximum value for shear? 4.75. Maximum absolute value for moment, 39. And we need to design the section using the maximum absolute values.